In the next three examples, we want to continue looking at finding the second derivative of a function, but now with problems where we mix in the chain rule, product rule, and quotient rule. In example 6, part A, we're going to find the first derivative of g of x. We have a chain rule problem where our outer function is x to the fifth. So to find dg over dx, we'll just set aside 2 as that coefficient, that constant multiple, and then we'll follow the power rule, which will become 5 times this inner quantity x cubed minus 1 raised to the fourth power times the derivative of that interior function x cubed minus 1. This will give us 10 times x cubed minus 1 to the fourth power, and the derivative of that interior function will be 3x squared, meaning our final result for the first derivative will be 30x squared times x cubed minus 1 to the fourth power. In part B, we want to find the second derivative, which still means we're going to take the derivative of our first derivative function. But now we have to apply the product rule because we have two functions being multiplied together. Meaning to find d squared g over dx squared, we'll find the derivative of 30x squared, which will be 60x, times x cubed minus 1 to the fourth power, plus 30x squared times the derivative of the second function, which will require an application of the chain rule. So finding just the derivative of x cubed minus 1 to the fourth, we'll get 4 times x cubed minus 1 to the third power times the derivative of x cubed minus 1. So we'll get 4 times x cubed minus 1 to the third power times 3x squared, or 12x squared, x cubed minus 1 to the third power. This means that our final result for the second derivative will be 60x times x cubed minus 1 to the fourth power plus 30 times 12, which will be 360 times x squared times x squared, which will give us x to the fourth, times x cubed minus 1 to the third power. In example 7, to find r prime of x, we need to apply the product rule again, since we have the product of two functions. Taking the derivative of the first function will give us 15x squared times the natural log of x plus 5x cubed times the derivative of the natural log of x, which will be 1 over x. X cubed over x will reduce, so we'll end up with 15x squared times the natural log of x plus 5x squared. To find the second derivative, the first term of our first derivative will require another application of the product rule, but then the last term will just differentiate by itself. So applying the product rule to the first term will give us 30x times the natural log of x plus 15x squared times 1 over x plus the derivative of 5x squared, which will be 10x. And then reducing that middle term, we'll end up with 30x times the natural log of x plus 15x plus 10x, which now allows the second and third term to combine as like terms. So we end up with 30x times the natural log of x plus 25x. No, plus 25x. In our last example, we have the natural log of x divided by x squared. So we apply the quotient rule, where we would get 1 over x times x squared minus the natural log of x times 2x. So that's the numerator after taking the derivatives of those functions where appropriate. All of that over x squared, that quantity squared. In the first term, our x in the denominator will cancel with 1x in the numerator, which will leave us with x minus, and then just reordering these terms and these factors in the second term, 2x times the natural log of x, all over x to the fourth power. We can factor out an x that's common in the numerator, which will leave us with x times the quantity 1 minus 2 times the natural log of x, all over x to the fourth, which will allow us to cancel with one of the x's in the denominator to get a final result of 1 minus 2 times the natural log of x over x cubed. In part B, we want to find the second derivative, meaning the derivative of the first derivative. This would be another application of the quotient rule. And personally, I'm not a big fan of the quotient rule. If I can use other strategies, I like to do that. So actually, we're going to go back to our result in part A and use some properties of algebra to rewrite this in a different format. Since I have a single term in the denominator, I can split this up as 1 over x cubed minus 2 times the natural log of x over x cubed. And then I can rewrite each of those values, each of those expressions in the denominator with a negative exponent. So I can rewrite this as x to the negative third minus x to the negative third times 2 times the natural log of x. Now I don't need an application of the quotient rule. I will need to apply the product rule to find the derivative of that second term, since we have one function which is x to the negative third and one function which is 2 times the natural log of x. But this first function differentiates very simply. That will be negative 3 x to the negative fourth, and then we're subtracting this entire next result, which would be negative 3 x to the negative fourth times 2 times the natural log of x plus x to the negative third times the derivative of 2 times the natural log of x, which will be 2 over x. In the last term, x to the negative third divided by x will reduce or combine, I guess, to give us x to the negative fourth power, because we would take that exponent in the numerator of negative 3 minus 1, the exponent in the denominator, to get negative 4. And then we'll also need to distribute this negative through to get negative 3 x to the negative fourth plus 6x to the negative fourth times the natural log of x minus 2 2x to the negative fourth. Our first and third terms are like terms, so we can go ahead and combine those to get negative 5x to the negative fourth plus 6x to the negative fourth times the natural log of x. From here we could factor out x to the negative fourth, since that's common between both terms, to get negative 5 plus 6 times the natural log of x, and we could rewrite x to the negative fourth as 1 over x to the fourth to get the final answer, negative 5 plus 6 times the natural log of x all over x to the fourth power. Or from the very beginning, we could have just applied the quotient rule, just to show you that there are alternate methods to get to the same result.